Hello and welcome to our first section, SVirt and Docker support. In this section you'll learn how SELinux can help reduce the risks of virtualization. Also, you'll understand how SELinux's policy is tuned to support these services. At the end, we'll look at securing Docker containers with SELinux. Now we move on to the first video of this section that deals with SELinux secured virtualization. In this video, we'll be introduced to virtualization and learn how to reuse existing virtualization domains. More and more system tools have built-in support for SELinux or use SELinux's features to further harden their own service offerings. When we look at virtualization, two open-source projects will definitely come to mind, libvirt and Docker. While the former supports full virtualization, the latter focuses on container management. Virtualization is part of many infrastructural services. When we look at service offerings today, we realize that many cloud providers would be out of service if it weren't for virtualization. One of the services that virtualization offers is isolation, which SELinux can support and augment quite nicely. When we look at virtualization, we look at the abstraction layers it provides in order to hide certain resource views, such as hardware or processing power. Virtualization contributes to the development of more efficient hardware usage, which results in better cost control, centralized views on resources and systems, more flexibility in the number of operating systems that the company can deal with, standardization of resource allocation, and even improved security services. There are a number of virtualization types around. The first one being full system emulation, where hardware is completely emulated through software. Native virtualization, where main parts of the hardware are shared across instances, and guests can run unmodified on them. Para virtualization, where the guest operating system uses specific APIs offered by the virtualization layer. OS-level virtualization or containerization, where the guest uses the host operating system or kernel, but does not see the processes or other resources running on the host. And the last one, application virtualization, where the application runs under a specialized software runtime. When we work with virtualization layers, a number of terms come up frequently, which are listed on your screen. The host is the operating system or server on which the virtualization software is running. The guest is the virtualized service, generally an operating system or container that runs on the host. The hypervisor is the specialized virtualization software that manages the hardware abstraction and resource sharing capabilities of the virtualization platform. An image is a file or set of files that represent the file system of a guest. And the last one, virtual machine, which is the abstracted hardware or resource set in which the guest runs. Virtualization comes with a number of risks though. If we ask architects or other risk-conscious people about virtualization, they'll talk about VM sprawl, challenges related to the secure or insecure APIs, the higher complexity of virtualized services and whatnot. Going over the challenges of virtualization itself is beyond the scope of this section, but there are a few risks that play directly into SELinux's field. If we can integrate SELinux with a virtualization layer, then we can mitigate these risks more easily. The first risk is data sensitivity within a virtual machine. Whenever multiple virtual machines are hosted together, you could have the risk that one guest is able to access sensitive data on another virtual machine. With SELinux, data sensitivity can be controlled through the use of MLS. Guests can run with different MLS labels so that the data sensitivity is guaranteed, even on the virtualization layer. Another risk is the security of offline guest images. Here, either administrators or misconfigured virtual machines might gain access to another guest image. SELinux can prevent this through properly labeled guest images, and ensuring that images of offline virtual machines are typed differently from online virtual machines. Virtual machines can also exhaust the resources on a system. On Linux systems, resources can be controlled through the control groups or CG group subsystem. As this subsystem is governed through regular file APIs, SELinux can be used to further control access to this facility, ensuring that the control groups maintained by Docker, for instance, remain solely under the control of Docker. Breakout attacks, where vulnerabilities within the hypervisor are exploited to try and reach host operating systems, can be mitigated through SELinux's type enforcement, as even a hypervisor does not require full administrative access to everything on the host. SELinux can also be used to authorize access to the hypervisor, ensuring that only the right teams are able to control the hypervisor and its definitions. Finally, SELinux also offers improved guest isolation, which goes beyond just the guest image accesses. Thanks to SELinux's MCS implementation, guests can be separated from each other in a mandatory approach. And with type enforcement, the allowed behavior of guests can be defined and controlled. This is a key capability used by hosting providers, as they allow running untrusted guest virtual machines. Now let's move ahead and see how to reuse existing virtualization domains. So I'm working on Fedora 26, which I've installed on Oracle VM VirtualBox, and I have already logged into it. With SVirt, Red Hat offers a reusable approach for supporting virtualization and containerization through SELinux. It does so through a number of domains and types that can be used regardless of the underlying virtualization platform. These domains and types are listed here. The vir td t domain is used by the hypervisor software. The SVirt t domain is used by guests that do not require general use of host resources. The SVirt QEMU net-t, SVirt KVM net-t, and SVirt LXC net-t domains are used by guests that require more interaction with the host. The SVirt TCG t domain is used by guests that require more flexible memory accesses. This is used for guests whose emulation or virtualization requires the use of a tiny code generator or TCG. The SVirt image t-type is assigned to the image file that contains a guest's data. The virt image t-type is assigned to image files that are not in use at the moment. The virt content t-type is assigned to image files when they're used in a read-only fashion. To enable some flexibility in what the domains are allowed to do, additional SELinux booleans are put into effect. To query these booleans and their current value, use the semanage boolean command, as we do it here. Let's type semanage boolean -l grep virt _. As you can see, it returns the current values, that is either on or off state for the respective booleans. For instance, to allow virtual machines to manage NFS files, we use the next command. Let's type set sebool -p virt _use _nfs on. Using SELinux booleans to control the confinement of virtualization domains should be carefully handled. Booleans influence the SELinux policy on the host level and cannot be used to change the access controls of individual guests. As such, the previous example, allowing virtual machines to manage NFS files, is applicable to all virtual machines running on the host. If security-sensitive operations have to be allowed for a guest, it's advisable to run those guests on an isolated host, where these operations are allowed, while running the other guests on hosts where the policy does not allow this particular action. Administrators can also use different SELinux domains for specific guests, fine-tuning the access controls for an individual virtual machine. How this is accomplished depends on the underlying technology, of course. The SELinux domains and the mentioned types, however, are not sufficient to implement proper confinement and isolation between guests. SVirt adds another layer of security by using multi-category security, or MCS. Within SELinux, some domains are marked as an MCS constrained type. When this is the case, the domain will not be able to access resources that do not have the same set of categories assigned as the current context. The SVirt implementation ensures that the virtualization domains mentioned earlier are all marked as such, MCS constrained types. This can be confirmed by asking the system which types are associated with the MCS constrained type attribute. Here's how we do it. Type seinfo -amcs constrained type -x grep virt _. So these are the types which are associated with the MCS constrained type attribute. Through the MCS constraints, SVirt enables proper isolation between guests. Every running virtual machine will be assigned two SELinux categories. The images that virtual machines need to use are assigned the same two SELinux categories. Whenever a virtual machine wants to access a wrong image, the difference in MCS categories will result in SELinux denying the access. Similarly, if one virtual machine is trying to connect to or attack another virtual machine, the MCS protections will once again prevent these actions from happening. SVirt selects two categories to allow a large amount of guests to run even when there are only a few categories available. Assume, for instance, that the hypervisor is running with the C10.C99 category range. That means that the hypervisor can only select 90 categories. If each guest only receives a single category, then the hypervisor can support 90 guests before allowing multiple guests to interact with each other. With two categories, however, the number of supported simultaneously running guests becomes 4005. In this video, we've learned about SELinux secured virtualization. In the next video, we'll learn about libvirt SELinux support.